in today's lesson. Democritus, ancient Greek pre-Socratic philosopher, primarily remembered today for his formation of an atomic theory of the universe. Democritus knew that if a stone was divided in half, the two halves would have essentially the same properties as the whole. Therefore, he reasoned that if the stone were to be continually cut into smaller and smaller pieces, then at some point there would be a piece which would be so small that it couldn't be divided anymore. Think of old Greek guy sitting on a stone olive branch.
So in his model that Ms. Diamantopoulos just explained, if you were to take one item and then keep raking it in half and half and half again, that smallest piece of matter, Democritus thought, he assumed that was what he calls the atom. So John Dalton in 1808, so we're talking 2 millennium after Democritus gave up his idea, basically John Dalton thought of this amazing idea, which we then coined into the atomic theory. So he believed in his atomic theory that all matter is made of atoms, and atoms are this indivisible and indestructible force. He also believed that all atoms of a given element are identical in mass and properties. He also believed that compounds are formed from a combination of 2 or more different kinds of atoms, and he believed that a chemical reaction is a rearrangement of atoms. And these 4 main topics are what we call John Dalton's atomic theory.
So we know today that atoms can be destroyed via nuclear reactions, but not by chemical reactions. Also, there are different kinds of atoms differing by their masses within an element that are known as isotopes. But isotopes of an element have the same chemical properties. They just have different masses.
So in 1897, there's a new scientist named J.J. Thomson, and he discovered the electron in a series of experiments designed to study the nature of electrical discharge in what they call a high vacuum cathode ray tube, which was an area being investigated by numerous scientists at the time. So the cathode ray beams, which are unknown at the time, are these negatively charged particles. And when Thomson placed a positive magnet next to the beam was attracted to it. This simply means that opposite charges are going to be attracting to each other, just like magnets. And a cathode ray tube, if you guys are unaware of what that is, those are the old style televisions. Those are the really big, really heavy TV sets that are very deep. So when you were to put them on a bookshelf or whatnot, they would stick 2 feet back. They were not light, they were not flat, they were these big, bulky items.
The negative electrons represented the raisins in his plum pudding model, and it contained a positive charge, the dough of it. So Thomson's model of the atom did explain some of the electrical properties of the atom due to the electrons, but failed to recognize the positive charges in the atoms as particles. So again, just that doughy area ends up being that positive section, and then we have these electrons that are just kind of stuck everywhere within it. The word atom represents something that is neutral, and so now that we have charges, this is still considered neutral because the positive and the negative still will balance each other out.
So far in our timeline that we've discussed, we talked about Democritus with his idea that anything can be broken into one unique part. Then the idea shifted to Dalton's, where now we have atoms of different types. And then with J.J. Thomson, we now are realizing that the atom is a positively charged thing, but it also has negatively charged sections.
And Dalton's theory is technically called the cannonball theory, because if you look at it, it kind of just looks like a cannonball.
All right, so cannonball for Dalton. And we also have the plum pudding for J.J. Thomson.
Ernest Rutherford in 1911 came up with the idea that atoms have a small charged nucleus surrounded by this very large empty space. And in that space, the electrons are circling within it, which this is now known as Rutherford's model, or the nuclear model, or the gold foil experiment. Sometimes it's referred to that as well.
In his gold foil experiment, Ernest Rutherford took a radioactive source, which we see in the bottom left-hand side, and he basically used that radiation to penetrate He used that radiation to then penetrate a very, very, very thin sheet of gold foil. In the process, he noticed on his detector that some of those alpha particles from the radiation source were then deflected, and they did not go perfectly straight through.
So now, before we move on, I just want to refer back to J.J. Thomson's theory. If this was J.J. Thomson's theory, all of those little radiation particles should have bounced completely back, and they don't.
That's because when you're looking at a cross-section, and a cross-section means if you were to slice something in half and examine the portions that have just been exposed, we're noticing that a lot of these alpha particles are passing straight through the foil. But if you notice path B and path C, these guys are being deflected. So if you have a positively charged ray of radiation being aimed at a neutral piece of foil and you're noticing deflections, that must mean something positive is making the positive ray bounce. That's the reason why, with Ernest Rutherford, he's then concluding in the nuclear model that the nucleus, or the center portion, is going to be positively charged.
So the gold foil experiment, things that you should take from it: positive particles were deflected and bounced off or bounced away. Particles passed completely through the gold foil. And from there, you'll see that this is how Rutherford and his colleagues created their theory of the atom. So because they passed through the foil, we say that the atom is mostly empty space. And because particles were deflected, we say the nuclear is dense or heavy in the center and has a very positively charged nucleus.
So now we're going from J.J. Thomson's plum pudding model, which again is just kind of like a random mixture of positive and negative sections, to now something way more organized. We have a very, very dense center core that's positively charged and lots of empty space where our electrons are floating around aimlessly.
And just to remember, the atom is still considered neutral because the positives and the negatives are still going to balance each other out.
So Niels Bohr in 1913 discovered that electrons travel like orbits, very much similar to planets, how they move around the sun. So electrons in different orbitals possess different amounts of energy. The closer the orbital is to the nucleus, the less energy it has. So if you have an orbital that's really far away, it has to have a lot of energy to stay attracted to something so far away.
And this is what we call the planetary model.
Because it looks like planets orbiting the sun.
Right. Erwin Schrödinger, he proposed the wave mechanic model. So imagine as the electron moves, it leaves a trace of where it is or where it was. This collection of traces quickly begins to resemble a cloud. So if you look at the diagram out in the corner, you'll see that this electron's kind of just bouncing all over the place. The probable location of the electron predicted by Schrödinger's equation happened to coincide with the location specified in the Bohr's model. So we call them now, instead of in Bohr we called them shells, now we call them clouds. This is what we call electron clouds instead of actual defined orbits.